Hello everyone. The goal for today's session is to present the final results of the BigHPC project. For this, we prepared a demo of the work carried out throughout the project. In order to provide some context and before the demo itself, we are going to recap the project goals, architecture, and main results. We are going to start on what was the motivation for creating such a project, then discuss the developed architecture, the integration of these components in one unified environment, the main results and takeaways, and in the end, the demo itself. Challenge and goals. 3 years ago, the BigHPC project was started with the ambition to provide better support for the increasing usage of artificial intelligence and machine learning workloads in HPC centers. One critical challenge for these workloads is to efficiently manage the available resources, since typically these applications are very storage intensive in opposition to the more common scientific workloads that run on HPC resources. Another important point is to make HPC more transparent to non-experts coming from the ML AI world who are not used to this type of environments. Also, we should be able to isolate each application from each other, allowing for fairness allocation between them. For this, the BigHPC project developed a novel management framework for big data and parallel computing workloads. To do so, three goals were set for the development of the project: development monitoring solution that would be able to monitor different HPC infrastructure, improve big data application development and better management of HPC computational resource, and also improve the storage performance and management for HPC services. BigHPC overview and architecture. The BigHPC project intends to solve the identified challenge and achieve the proposed goals, resourcing to three main components: a virtualization manager responsible for store, curate, and manage the container files to deploy, and also responsible to launching them in the cluster if there are available resources; a storage manager that will keep track of I/O requests being made to the shared storage resources, for example, the shared parallel file system, and enforce QoS policies to improve I/O performance for applications using such resources. And last, a monitor backend that will inform both the storage manager and virtual manager of the cluster status and workloads in real time, while also storing data from workloads run for later analysis. Here we can see the detail of the different components, where users and sysadmins are intended to interact with the virtualization manager, either to launch their workloads or upload a new container with the desired job. The usage of a containerized solution is of key importance, since it will allow a more straightforward path from the user machine to the HPC. The virtualization manager then launches the containerized workloads on the compute nodes, while the storage manager ensures the desired QoS policies for the I/O requests being issued by these containers is also applied. This is crucial since big data workloads are storage bound. The monitoring backend has access to the compute nodes and storage nodes via the InfiniBand network to capture the desired metrics. These metrics are then fed to the users and sysadmins and can be queried by the virtualization manager or storage manager. Components integration. In order for these three components to work together, since each one translates into multiple projects that are developed among different teams, all the projects need to be merged into a final deployment, where all of them will work together. These components can be split in two groups by their function and location on the HPC: service that run over a Kubernetes cluster on the left column, or local applications that run on compute nodes on the right. Our preliminary step was to specify the several software environments and their requirements for the runtime. For that, two main testbeds were defined: a development testbed and a preview testbed. The development testbed applies the steps required for software quality analysis, while the preview testbed provides the real environment to validate the current release. The goal, in the end, is to have a release of the software ready for production. GitLab was used as the support platform to manage the delivered workflow, allowing for the implementation of DevOps practices such as continuous integration and continuous delivery. In order to interact with the virtual manager, a web-based front-end was developed in parallel with a command line interface. This allows to upload and submit the desired workloads or perform other admin tasks. In this example, at the right, we can configure a BigHPC partition. Main results and takeaways. Along the course of the project, several prototypes were concluded: Bio, the virtualization manager, Hector, Monica, Shepherd, and Paddle. And the following list enumerates the papers published by the BigHPC project along the 3 years of duration. The main takeaways: the BigHPC project developed a unified framework for running parallel and big data jobs at HPC centers, resourcing two containers for easier portability and deployment, what we are about to see in the demo, while implementing storage QoS policies to ensure fairness and avoiding I/O bottlenecks. This, combined with the monitoring and visualization tools to understand the cluster's usage. And now we can go to the demo.
In this demo, we will explore how one can leverage the BigHPC framework to launch TensorFlow jobs for training AI models within a containerized environment. We provide an interface that allows users to upload the container image they want to execute. The fields for uploading the image are standard and can be filled with values similar to the ones shown here. However, for the purpose of this demo and to save time, I have already uploaded the TensorFlow image that I will demonstrate. To submit a job within this framework, users simply need to complete the provided interface by filling in fields like the job name, the desired container image, and other standard values required for the job's execution on the compute nodes. One notable field among these is the QoS ID value, which is an innovative feature of a framework. This value enables users to assign a specific priority to their job, determining the bandwidth allocation it can utilize when accessing shared storage resources like the parallel file system, listed for example in this demo. I will now submit a job to the Virtualization Manager, which will consequently launch it on a compute node. Additionally, I'll launch 3 more jobs with similar parameters, with the only distinction being their respective QoS priorities. For this job, I will assign it a QoS priority of 2 and launch another job with the same priority. It is important to note that different jobs can have the same priority. This last one will be assigned a priority of 3, so it will have the highest priority. Note that these TensorFlow jobs will use data stored on a shared parallel file system to train their respective AI models, which means that they will compete with each other for access to lesser resources. Again, jobs with higher priority will have access to more storage bandwidth. Some time has passed, and the Virtualization Manager has successfully launched the jobs on the compute nodes. These jobs have been running for a few minutes now, and we can monitor them through our dashboard. Our monitoring system provides an overview of various resources, including the CPU, memory, network, GPU, and parallel file system, amongst others. But given that we are running TensorFlow jobs, it is relevant to focus on resources like the GPU. We can observe in our dashboard metrics such as its usage and temperature. However, what is particularly interesting is to look at the parallel file system usage, since it is a resource shared amongst the jobs. Here, we can observe the usage of each job. In particular, the job with the lowest priority shows the lowest file system bandwidth, while the job with the highest priority demonstrates the highest. And obviously, the jobs with the same priority have a similar bandwidth. To summarize, the demo that I have presented is only made possible by the 3 core components offered by our BigHPC framework. The Virtualization Manager facilitates the launch of containerized workloads on the compute nodes. The Storage Manager ensures the enforcement of the desired QoS policies for shared storage resources at HPC infrastructures. And the monitoring backend provides a comprehensive view of the system's current status, enabling the monitoring and assessment of various metrics and resource utilization in real time. Thank you.